So I don't know if this time it work. Okay, just try. And they said they have improved this system. Okay, if this time still can it cannot work, and okay, some of it okay now because they try to improve the system. They have tried to improve the system, and maybe this time it could be okay. But if you still cannot, you can just tell me, and I can help you with this. Okay. Okay, some of you still cannot. If you still cannot scan that, you can tell me and I will help you with that. Okay, I know if you can still cannot use that QR code, you just send me a message and I will help you with that.
Teacher, I did send you. Can you please check
Okay,
the WeChat?
okay. Uh, okay. So if you still cannot use that QR code, you can send me a message, and I will help you to mark that after the class. Okay. Okay. So okay. So let's go on. So last time we have introduced the uh, And we have also introduced the instantaneous acceleration. It's the limit of average acceleration as t approaches 0. So you can also use dv over dt to calculate the acceleration. So this example tells how to calculate v and a when we know the function of x. Okay, so there is a very special kind of motion, and it's also very common in our daily life, the constant acceleration. If a particle is moving in a straight line with constant acceleration a, and at t is equal to 0, the velocity is v0, and the displacement is x0. We want to determine the velocity xt and displacement vt and displacement xt as a function of time. So this is a very special kind of motion, the motion with a straight line with constant acceleration. So just like a free fall object, it has a constant acceleration g, like that. So that is very common in our life. So if we can calculate v, determine v and x as a function of time, that would be a conclusion which is very useful for us. So this one is different from previous ones. So, but we can start with the same equation, just like here. According to the definition, v is equal to dx over dt, while a is equal to dv over dt, according to the definition. So we always start with these two equations. So if we want to find out the function vt, we just choose to start with this one. So a is equal to dv over dt. So now we know a is a constant. We want to solve v, so what we are going to do is separate the variables. A is something we know, it's not a variable, it's something we know, it's a constant here. And v and t are two variables. We are going to separate these two. That means we need to let each side of the equation with only one variable. So what we are going to do is put dt to this left-hand side. So that is a dt is equal to dv. So we separate the variables. Each side, one variable. So, and then we can take an integration on both sides. The integration. So, well, for the time, start with t is equal to 0. So here is 0. And at time 0, the velocity is v0. So that's why here is v0. And from t is equal to 0 to some time t, and when the time is t, the velocity may be v. So, and then we calculate the integration on both sides. So on this side, that is at, and on this side is v minus v0. So okay, you can also say this is vt because it's a function of t. So then you can get vt is equal to v0 plus at. Okay, so that's v. So then we are going to determine x. So if you want to determine x, you need to use this one. So v is equal to dx over dt. And then we substitute this one into this equation. That's which is equal to v0 plus at. The next step, still we want to separate the variables, because according to this equation, two variables, x and t. v0 is the initial condition. We know v0. So we want to solve x. So we put dt to the right-hand side. So that means dx is equal to v0 plus at times dt. Okay, and the next step, still take the integration on both sides. So t start from t is equal to 0. So when t is equal to 0, the displacement is x0. So that's why here's x0. And when the time is t, there is xt. Okay, then we calculate the integration on left-hand side is xt minus x0, which is equal to, on the right-hand side, so when we calculate the integration, this one is v0t and plus half at squared. So then you can get xt. So xt is equal to x0 plus v0t plus half at squared. So these two equations can be applied to the situation when something is moving in a straight line with constant acceleration. So these two equations may be useful. So let's see this again. So we use calculus. So start from here. Always start from this equation, or v is equal to dx over dt. And we separate the variables. Each side, one variable, and then we calculate the integration. Remember that this one and this one should be the quantity at the same time. So time 0 corresponds to v0. Okay, and you calculate the integration, so v minus v0 is equal to at, and we can calculate, that's why we can find out v. And when if you want to find out x, that's the same method. You write you can use this equation dx over dt and then separate the variables and take the integration on both sides. And the v, you can use the result in previous slide. So you can find out this. So these two equations are very useful. So for constant accelerations, we have got these two, this one and this one from previous example. So, but there is one more equation which is also very useful. So this one, this equation, the third one, tells us the relation between speed and the position. So x is the position and v is the speed. So how can we get this one? By using these two. So by using these two, we can cancel t. When we cancel t, you will get this one. So just like from the first one, we know t is equal to v minus v0 over a, and substitute t into this equation, you will get this one. And this equation, v bar, means the average speed. The average speed is equal to half v plus v0. So that's the average speed. So these equations, especially these three, are very useful because constant acceleration, moving with constant acceleration, is a common motion in our daily life. So we are going to use these equations or the calculus to solve the problems. So when you want to solve, well, first you need to read and read again the whole problem carefully before trying to solve it. Then we need to decide what object or several objects you are going to study and for what time interval. And usually we need to choose initial time to be t is equal to 0. That will be very helpful if you choose the initial time to be t is equal to 0. Although we will draw a diagram or a picture of this situation, and we choose the coordinates, the x, which direction is the positive direction, which is negative. So because when you deal with the quantities like vectors, they have direction and quantities and magnitude. So you need to draw a diagram and tell the others which direction is a positive direction, so that we can use positive and negative to indicate the direction. Positive means the direction of this vector is the same as the direction you choose to be positive. And if you get a negative quantity, that means the direction of this vector is in the opposite direction. So then you need to find out what are known or given and what is unknown or what you are going to find out. Okay, then we try to find the equation or a principle that can connect those known and unknown things. Then we can use this equation to calculate that. Usually the result may be not reasonable. Sometimes it may not be reasonable. So you will try to find out if this result is the real correct result. Sometimes there may be several solutions and only one solution is the correct one. Okay, so that's why we say, okay, after you calculate, you think about it, is that reasonable? Does that make sense? Because sometimes the order of magnitude of your result will tell you if you have made some mistakes in the calculation. For example, so in one experiment, I asked the student to measure the width of a slit using a microscope. So, but after that measurement, one student calculated his results and showed me, okay, he told me that his result is that the width of the slit is 5 millimeters. So then I asked him a question. So if the width of the slit is several millimeters, why you have to use a microscope to measure that? So if you need to use a microscope, that means the size is very, very small, right? So it cannot be several millimeters. if you want you want to measure the length of something several millimeters, you just use a ruler. That's okay. You don't need a microscope. So you use a microscope, that means it's very small. It cannot be several millimeters. That's not reasonable. So that's why after your calculation, you need to think it over whether it is reasonable. So and another thing is keep track of the unit. This will help you to avoid mistake in calculation. Okay, let's look at this example, a runway design. For example, if you are going to design an airport for small planes, so one kind of the airplane that might use this airfield must reach a speed before takeoff at least 100 kilometers per hour, which is also 27.8 meters per second. And you can accelerate at 2 meters per second square. So if the runway is So if the runway is 150 meters long, can this airplane reach the required speed for takeoff? That's the first question. The second, if not, what minimum length must be the runway have? So let's check the first question. According to our method, we have read this problem, and maybe you should read it again. And if the runway is 150 meters long, is that enough? So first step, we draw a diagram, right? So we should build a model for this problem. So this aeroplane, so we treat it as a particle. And we choose to start from here. Well, the x is equal to 0, which means origin. And we start from origin. And this direction is the direction of the runway, which is also x direction. We choose this direction to be the positive direction. And the speed is in this direction. The velocity should be in this direction. Okay, and this aeroplane, well, this is the model and axis and the coordinate. And then we are going to find out what is known and what is wanted. And we know, okay, we choose to start from here. Well, x0 means the initial position is 0. And initial velocity should be 0 because the aeroplane should start at rest, right? So that's reasonable. So what we know, the V0 is 0. So, sometimes in a real problem, they will not directly tell you what the initial condition. You need to find out from description, right? Or from the what you know in your daily life. So when a airplane wants to take off, it starts at rest, right? Originally start at rest. So that's why we choose V0 to be 0. That's reasonable. And we know now the runway is 150 meters long, and the acceleration of this airplane is 2 meters per second. What we are going to calculate is the final speed v at x is equal to this 150. So it starts here and accelerating and finally reach here, and we want to calculate the v and see if v is greater than the required speed. If it is greater than the required speed, it can take off. Otherwise, it cannot. So, okay, so we know all these quantities, and we are going to find out this one. So we need to find out the equation. So which equation we are going to use? Let's check these equations. So we know V0, we know X0, we know X, and we know A. So this equation is the equation that we want. It collects all the variables that in this problem. So that's why we choose this one. This one can help us. So we choose this one, and this one will help us. Okay. Sorry. Let's go on. Sorry. So, okay, we choose this equation. And we substitute all the known quantities into this, and we can calculate the V. So now V is equal to, sorry. Okay, now V is equal to this, 24.5, which is smaller than the required speed. The required speed is 27.8. Sorry. The required speed is, let's see here, is 27.8. So that means 150 is not enough. We need a longer one. So how long should be enough? So maybe let's check this. You can calculate it by yourself. What's the minimum length? And then you can tell me which one is the best solution. And on the screen, you can tell me on the screen which one is the best solution. There are several solutions. If you are a designer, which one you will choose? So try to calculate. Then we know 150 is not enough. So how long is the best? Try to calculate it by yourself and tell me your choice. So just you can use the same equation in previous one, but in this one you are going to calculate how long is enough. That means we know like Vx0 is still 0, V0 still 0 meters per second, and we know the final velocity should be 27.8 meters per second. And A is equal to 2 meters per second square. We are going to find out. This is known. And this is wanted. What we are going to find out is how long. That's X. We are going to find out X. And you can use exactly the same equation, but not this time we are not going to calculate V, but we are going to calculate X. Still that equation, like V square minus V0 square is equal to 2A x minus x0. But this time we are going to find out x. We're going to find out x, not v. So try to calculate it by yourself and tell me what's your choice. You can tell me your choice on the screen, or you can tell me your choice in the group. That's also okay. 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 So
Shabir,
okay. So some of you have tell me a choice. Some of you choose B, and some of you choose C. So let's see which is the best. So we use this equation, right? And we know V. We know V is equal to 27.8, and acceleration is 2. So x0 is 0. So that's also x. So 193 is the result. But is that the final result? So it's correct that by calculation, that's the result. But remember, we get this result when we treat the plane as a point. Our model is a point. But a real plane cannot be a point, right? A real plane cannot be a point. So usually, a real plane is at least several meters. So that's why 200 would be better. Because when you look back, design an app for small planes. Small planes, several meters, that's reasonable. So why not this one? 500. Because we do not have that large planes. So the largest plane in the world is 85 meters long. No plane can have length longer than this. The largest plane on the Earth is 85 meters long. So that's why we do not need this one. We only need 200. That's the 200 is enough. But you cannot use this. This is not enough, because if it is a point, then maybe that's enough. But it's not a point. It's several meters long. So actually, this one is not enough. So this example tells us, so sometimes we build a model for our calculation. So after the calculation, if you want to apply your result in real world, you need to consider the real situation. So not we build the model to help us to understand this. But when you apply your result to real situation, you need to consider the real situation. So that's about this one. That's why 200 is more appropriate. Okay, let's see this. Two moving objects. Police and the speeder. A car speeding at 150 kilometers per hour passes a steel police car, which is immediately takes off in hot pursuit. And using a simple assumption such as that speeder continues at constant speed and estimate how long it takes the police car to overtake the speeder. If the speed car can accelerate, if the police car can accelerate from rest to 100 kilometers per hour in 5 seconds, then estimate the police car speed at that moment and decide if the assumption is very reasonable. So usually when you meet a real problem, the first step you need to, as we read the problem, and then you build a model and you draw a diagram and then you calculate that. So when you build a model, you need several assumptions, right? So because the real situation is complicated. So let's take a rest. Okay, so let's go on. So, for real problems, so it's really complicated. We need to build a model to ignore something which will not affect our result. But after the we build a model, we will calculate that, and when we look back at our result, we need to think whether your assumptions were reasonable, because sometimes you assume something and simplify the problem and calculate the result. The result may not affect the truth, right? So it may be something you ignored will affect the result, or something you treated with a simple model, but the reality is far from this. So that's why sometimes after the calculation, we need to look back whether all these assumptions are reasonable. So just like this one, so a car is speeding at 150 kilometers, and maybe we treat it as a constant speed. So the acceleration, and the police car is accelerating, so they want to catch that speeder. So it originally at rest and accelerating from rest to 100 kilometers in 5 seconds. So we can calculate the average acceleration of this police car, and this is the speed, and this is time. And remember, we should transform all the units into international units so that we can keep track of the unit. So 100 kilometers is about how we need to transform it into meters per second. So that's why we need this step. We are going to transform 100 kilometers in. If we direct calculate this, that we would be 20, right? But the unit is kilometers per hour over second. So we need to transform this part into meters per second. So 1 kilometer is 1,000 meters. And an hour is or we can say 3,600 seconds. So we can transform this into international units, and this gives us as the result 5.2 meters per second squared. Okay, that's the acceleration of the police car. And the position of the speeder. So the position of the speeder is and it is constant motion, constant acceleration, but the acceleration is 0, so that's why AS is equal to 0, and this one is equal to x. S is equal to V0 st. So t is the time when we catch that speeder. So t is unknown, maybe it's unknown. So this part is 0, and V0 is 150 kilometers per hour, which is equal to 42 meters per second. We need to transform all the units into international units. And the position of the police during the same time interval is a constant acceleration. But AP is not 0. We have calculated AP in previous slides, and now we get this. Because V0 police is 0. Originally, the police car is at rest. So, what means the police has caught the speeder? If they are at the same position, right? If they are at the same position, that means the police have caught the speeder. So that's why we should set XS is equal to xp. When they are at the same position, that means the one catch the other one. Okay, so this can help us build the equation. This one is equal to this one. Then we need to solve t. There are two solutions, one of which is t is equal to 0. Obviously, that's not the solution, right? T is equal to 0 is not the solution. So the second one should be correct. T is equal to 15 seconds. So, okay, this is the result. After 15 seconds, the police car will catch the speeder. But this is our model, but we should look back whether this model is reasonable. It's reasonable. So then we can calculate this speed of the police car at the moment that when he catch the speeder. And according to that equation, v is equal to v0 plus at. This can help us to calculate the final speed of the police car, and is 84 meters per second, which is also 300 kilometers per hour. That's something not reasonable, because if we are driving with such a high speed, it's very, very dangerous. It's very, very dangerous. It's extremely dangerous. It's not reasonable. It's highly dangerous. Especially, you are a police car. You cannot break the rules. You break the rules, right? You should follow the rules. So the other can follow the rules. If you are moving, so the speeder is only 150, but you are 300. That's not reasonable. So police car cannot run that fast. Cannot run that fast. It's not safe. So that's why maybe in the movie, usually the police car cannot catch the speeder, because the speeder can break the laws, but the police cannot. That means this is not reasonable. This is not reasonable. So this example tells us sometimes when you finish your calculation, you can look back and check whether your assumptions are reasonable. So we can't assume the police can run that fast. So it actually it cannot catch the speeder with such a short time. And there's another thing which is also not reasonable. So when the police find, okay, this car is running fast, I'm going to catch that guy. So you need to use something like a siren, right? So the speeder, when he hears this, he will not keep the speed. He will slow down and stop. And so if you do not stop, they will shoot you, right? So that means real situation is not so simple. Sometimes when you look back after the calculation, you will find out, okay, that's not reasonable. So, okay, so that's previously we have investigated two problems, and now we are going to investigate another one, which is a special motion with constant acceleration, the free fall. So the free fall, there's a very important question, whether the free fall motion is associated with the mass of the falling object. First, we know when we talk about free fall, that means we will ignore the drag force of the L. When we ignore the drag force of the L, we drop some object originally at steel, and that is free fall. And whether this motion will be affected by the mass And we can check that. So it's let's choose here as a direction like x, and originally at here, which is x0 is equal to 0, and we release this object, it will fall, and the v0 also 0. So according to our equations, we know v should be equal to v0 plus at, right? Vt, like. And here a is the acceleration of the object near the surface of the Earth, which is, we can say here's a is equal to g. G is the acceleration near the surface of the Earth, and almost constant. So should be equal to v0 plus gt, and v0 now is 0, and it should be equal to gt. The speed does not affected by mass. And also the, let's say, the displacement, right? X is equal to like x0 plus v0t plus half at squared. And x0 is 0, v0 is 0, so this part 0. And only half at squared, a is equal to g, which is half gt squared. And according to these two equations, the speed is proportional to time, and the position or displacement is proportional to the square of the time. It has nothing to do with the mass, which means you have two objects, you let it fall from the same place, and one is heavier, one is lighter, they will hit the ground at the same time. So it is said that Galilei Galilei did this experiment on Pisa Tower, but no one knows whether he really did this to conduct this experiment. But these equations can tell us they should arrive at the ground at the same time, no matter what's the mass. So because the displacement is proportional to t squared, and here the g is the acceleration near the surface of the Earth due to the motion, the gravity and motion of the Earth, and usually it's about 9.8 meters per second square. Sometimes you can use 10 for a rough calculation. You can use 10. Okay, and this motion is really useful. Like here, two guys, and here's a well, and one asked the other, "Do you know how deep your well is?" And then this guy said, "No, not really." And this guy picked up a stone and release it and count 1, 2, 3, 4, 5, and finally 60. He after 60 seconds, he heard a sound when the rock hit the bottom of this well, right? And by this 16 seconds, actually he can calculate the depth of this well, because according to that equation, the depth should be of the well should be about half g t squared. Here t is 16 seconds and g is about 10, and he can roughly estimate the depth of the well. Okay, that's useful. Sometimes if you do not want to know exact how deep it is, you can do that. The longer the time takes, the deeper, right? So if you find a well and maybe you think, okay, whether I should go into that and check what is inside it. And the first thing you need to do is throw a stone to check whether it is safe. Because if it is so deep, don't try to get into that well, right? If you throw a stone, after 10 seconds, no response. That means it's extremely deep. And that's estimate about it's only 10 seconds. 10 seconds. 10 seconds square is 100. Right? 100. And this one is 10. So if 10 seconds, that means 1,500 meters. That's it. That's deep. 1,500 meters deep. Only 10 and 16 much greater. So you will not want to get into that well. Okay, and especially you cannot see that, but even you cannot see, but you can use that stone to help you to find out, okay, whether it's so deep, it's safe, whether it is safe. So and this method, sometimes when you travel to some place like near the sea, maybe you see, okay, that is near sea is water like that. You don't know. Maybe sometimes even near the sea, there can be a valley in the water because the geological change. Originally, here is a mountain, and due to the geological motion, it maybe go deep into the sea, and it is near the seashore, and you will not know that, right? You can see here are rocks, and here is some water, and you do not know maybe they're hundreds of meters deep, even near the seashore. So now then you can throw a stone. Even in the water, it's moving slower, but if it takes very, very long time for you to hear the song, that when you hit the bottom, or you can never find out the song, that means it's extremely deep. Sometimes this will happen near the seashore, but it's really deep. It's really deep. Okay, so this is useful. So this chapter, we have investigated the kinematics in one dimension. So we should use, there are several definitions like velocity. We use calculus to define velocity, and acceleration. We also use calculus to define that. So based on these definitions and the calculus, we can work out these equations for constant acceleration in one dimension. These equations are useful, especially the first three. Okay. So this is the this chapter 1 in one dimension. So okay. So then chapter 3, we will move on to 2 dimensions. So kinematics in 2 dimensions. But why not 3? Because 3 and 2, it's almost the same. The method is almost the same. So if you know how to deal with 2 dimensions, you will know how to deal with 3 dimensions. So in this chapter, we will investigate these three topics: the vector and scalars, and the vector kinematics, and the projectile motion. So, vector in Chinese we call it 矢量, a quantity which has direction as well as magnitude. So vector in Chinese 矢量, 矢 in Chinese means arrow, 矢 in Chinese means arrow, and 量 quantity. An arrow with quantity, a quantity with arrow, that means has direction and magnitude. So, scalar in Chinese we call it 标量, 标量 scalar. Scalar has no direction, as it has no direction. Okay, we use different symbols to indicate a vector or scalar. Like here, A, we use a boulder face, or an arrow on the top. These two, we mean vector. If like this, only Italian type, we mean scalar. So when you read a book, this boulder face or an arrow on top of this letter, that means vector. Italian type means scalar. So if you move a vector parallelly, parallel motion of a vector does not change the vector, because a vector, like an arrow, the length is the magnitude, the direction is the direction, and no matter how you move it parallelly, it will not change the length, and it will not change the direction, right? So that means parallel motion of a vector does not change the vector. So in this chapter, because we are going to investigate vector kinematics, so we need to know how to calculate with vectors. The first is the addition of vectors. So that means we have two vectors, A and B. What is A plus B? There are several methods to help us to calculate A plus B, one of which is called tail to tip. So if this is A and this is B, from the tail to the tip, C is equal to A plus B. Vector C is equal to vector A plus vector B. So that's why we call tail to top to tip, because from the tail of A to the tip of B, that's A plus B. So A plus B is, this one is A plus B. You use a triangle to help you to calculate A plus B. And there's another method, just like here's A and here's B. So we know parallel motion of the vector will not change the vector. So we can move it to here. And if we move it to here, we know this C is the A plus B. And that's why also here is also A plus B. So you can either use this triangle and also use this. That's the same. Okay, so there are several rules, like A plus B should be equal to B plus A. And A plus B plus C, the summation of A plus of A and B plus C is equal to A plus summation of B and C. And we can define zero vector. So zero vector is then vector has zero length, but it can have a direction, So that's called zero vector. We write a zero and an arrow on it to mean zero vector. So A plus A, zero vectors, zero A. So this is the zero vector. And sometimes you need to calculate a vector multiply A is 2A. The direction will not be changed, only the magnitude will double. So if a constant C times A, a vector A, that it has the same direction as A, but C times the length of A. So a constant change the length. How many by how many times? By this constant times. And we can also define negative vector. So what is minus A? So minus A has the same length as A, but the direction is in the opposite direction. So that's negative. So if we have defined the negative vector like this, the subtraction of vectors. So A minus B should be equal to A plus minus B, right? So we can use a triangle or something to like similar to help us to calculate A minus B. So here's A and here's B. So A minus B should be equal to A plus this minus B. So minus B is in the opposite direction, same length. Okay, so we calculate this one plus this one according to tail to tip. From the tail to tip, this should be A minus B. This should be A minus B. So when you calculate A minus B, so that's something like this. This is A, this is minus B, and this is A minus B. So, but this one, this is not that convenient because you need always to find out the opposite direction. So if we want to find out a method that we do not need, if we can find out another method, we don't need to find out minus B, the direction of minus B. We do not need the opposite direction. If there's a method to help us, that would be better. Just like this. So if this is A, so the same direction, same length, this is also A. And this is B. And what is A minus B? This one, the length should be equal to this triangle and this triangle. Actually, they are the same, right? So if the length of this is B, the length of this is B, and this length is A plus B. So this length should also be A plus B. And this one should be parallel to this one. So if we choose the arrow to be in this direction, that should be the same. So then we move this away. So that's how we calculate the subtraction of vectors. We use a triangle. This is A, this is B, and this is A minus B. So what is A minus B? A from the tip of B to the tip of A. That's A minus B. Use a triangle. This is A, this is B. And from tip of B to the tip of A, that's minus A minus B. So this is not tail to tip, it's tip to tip, right? Tip to tip. But we use a triangle to help us to calculate A minus B. Okay, so but you cannot always draw a triangle. To solve a problem with triangle is not so simple unless there is one angle which is equal to lighted them by complements. So just like here, if this one is A, we can resolve it into X and Y complements. So why we can do this? This one is simpler. Why? Because you can see here, if this point on this AXY coordinate, if this coordinate of this point is XY, you will find out the length of AX actually should be equal to X, and the length of AY actually should be equal to Y. So if we define something which is called unit vectors, so unit vectors means the length is 1 and in specific directions. Like if it is in X directions, it's I, Y direction is J, K direction is K. So this, we can express this vector A in another way. It's AXI, AYJ, and also AXI plus YJ. Because AX is equal to X, the coordinate X, and AY is equal to the coordinate Y. So that can help us to use the coordinate to express the vectors. That's why we need the complement form. So, okay, we know the complement form. And now we want to know how to calculate the addition of vectors. So we have two vectors, A and B. That's the complements, AX and BX, AY and BY. And A plus B, actually, the comp is just the calculate the addition of the complements. So you can see the X complement is AX plus BX. Y complement AY plus BY. Or you can just say XA, XD, XY, YB. That's the same. This is simpler because we do not need a triangle. We do not need a triangle. There's nothing to do with the angles. And it's exactly the same with if you use a triangle. So directly calculate the summation of the coordinates. That should be okay. You don't need to use a triangle, because if this angle is not 90 degrees, it's very hard for you to solve the triangle. Like if you know length of this, even though the length of this, you know one angle, you want to calculate this length. That will be extremely complicated. So all the calculations can be done with complement form. So complement form is simpler. Okay, so we have that tool, vector and complements. We can use this to help us to determine, to describe something in a motion with 2 dimensions. So like the first quantity, 位置, position, 位置. In Chinese, we call it 位置, position. Originally, we use a coordinate to describe the position. But if in vector kinematics, we need the 位置, the position, to be a vector. So how can we transform xy into a vector? That is very easy. We draw an position vector. The vector is equal to xi plus yj. I and j is the unit vector in x and y direction. So the yx component of r is equal to x, and the y component of r is equal to y. So that's xy plus yj. That's exactly the same as you use the coordinates. Both these 2 ways, 2 variables, x and y, right? But now we transform the coordinate into a vector. If it is 3 dimensions, that's xi plus yj plus zk. So that's the position. And the displacement. Displacement is the change of position. So now if we use the position vector to describe the position, and this change of position should be change of the vector from A to B, point A to point B, and that means from this vector to this vector. Or RB minus RA or R2 minus R1. That is equal to this. Tip to tip from A to B. A vector from A to B means displacement. Okay, and if we use the component form, that means the x component is the delta x, y component is delta y. This can help us to collect the two-dimensional problem with the one dimension. Because for each delta x or delta y, that's a kinematic problem of kinematics in one dimension, right? And we just for two dimensions, the kinematics in two dimensions, we can use the component form to change it into two calculations in one dimension. So even for three dimensions, that is the same. We just change it into component form. And for each component, that's a one dimension problem. And just like what we did in previous chapter, we need to define displacement and distance. And almost the same. Sorry. Displacement does not equal to distance. But there is another case, very special case, when delta t, the time interval is, when temperature approaches zero, it means in a very, very, very short time, these two can be the same. But usually they are not the same. And displacement, delta r. Okay, delta r. What does delta r mean? Here, delta r means change of the displacement of the position vector. Here, like start from RA to RB, the change is delta r. So delta r means the displacement vector. And here means the magnitude. The magnitude of displacement does not equal to the distance. Yes, displacement in two dimensions. Here means in two dimensions. Displacement. Here delta r arrow means displacement in two dimensions. Here two dimension problem. Only two. Okay. 3D, that's the same. 3D, that's the same. We use delta r arrow in 3D. Also is 3D. Okay, so now let's finish this example. After finish this example, we can finish all today. So if a very bad flies from coordinate this place to a coordinate this place, what is the displacement? So this example will show you that if you use the components form, that would be much simpler. But if you want to calculate with triangles, that would be extremely complicated. So if we use components form, the displacement should be equal to x for x components, that's x2 minus x1. Y components, y2 minus y1. Z components, z2 minus z1. So we just use for x2 minus that's 6 minus 2, that's 8, right? So we substitute digit into this. And this is the final result. You don't need to calculate the length and angle of the vector. Components form is the result. You can use the components form to express the result. And this calculation is very simple. You can, maybe if you are familiar with this, you can calculate all this in your mind, right? You don't need to write down. You can calculate this in your mind. But But if you do not use a component form, you treat this as the arrow with a certain length, and this is another arrow with certain length. There are two arrows. You use these two arrows to form the you have and the displacement arrow, the displacement vector, and three vectors to form a triangle. And then you want to solve this triangle. That would be extremely complicated. So that's why we tend to use the component form, because the calculation can be much simpler. So okay, let's stop here today. Okay, that's all for today. Okay, see you next week.